Hello, so today we'll be looking into Jpeg compression. It is a lossy type of compression technique. Lossy means there will be certain loss of data which is redundant, which is not perceivable for the naked eye, or which is, again, as I said, it is not conveying any something new for us. So such type of data can be done without, so as to compress the image in size. It is a widely used technique. Jpeg stands for Joint Photographers Expert Group. Now this is the block diagram of Jpeg. At the input we have got an 8x8 block, which is not the image but it is a part of an image. It is a chunk of an image which is fed to a DCT, that stands for discrete cosine transform, which then again is fed to a quantizer. At the input of the quantizer we have a quantization table, which is then given to an entropy encoder, which will encode the output of the quantizer. It could be any of the entropy encoder. We have got Huffman coding here. There's also arithmetic coding. Huffman coding is already done in your digital communications. As of now I'll not be covering it, but if you need, please let me know. I'll record a different video for Huffman coding. After that, then we also have something called as line encoding, wherein we have run length encoding, which is again a new topic I'm assuming, which also I can cover it in a short video if you like. That is being transmitted at the receiver. It is received and the reverse process takes place, wherein you have the decoder, Huffman decoder, then we have dequantizer. Again the same quantization table is being fed to the dequantizer. Then the inverse discrete cosine transform takes place and the output. Now first of all, why do we need to divide images into regions of 8x8 or chunks of 8x8? It is first of all efficient. You're dividing your entire image into smaller regions so that they are efficiently converted to frequency domain, which can be analyzed in a smaller regions in a more optimistic way, rather than dealing with the entire image, which becomes too time consuming process to convert an entire image in one go from time domain to frequency domain. And too short, and if you are making the chunk smaller, if you are dividing it into smaller regions, let's say 4x4 or 2x2, then also it becomes too time consuming, since you have to perform the conversion from spatial domain to frequency domain many times. So this is found to be an optimistic size of 8x8 to divide from spatial domain to frequency domain. That is what is done by DCT, that is discrete cosine transform. Now we are dividing it into frequency domain because we want to analyze certain, like what is the content of the low frequency region in that part, what is the content of the high frequency region, because for the naked eye the smaller details are not as perceivable or not as important as the bigger details. And in frequency domain, the bigger details, not the details I would say, but the surfaces constitute the low frequency components, whereas the smaller details, a noise, a speckle, a edge, they constitute the high frequency component, which are not so clearly perceivable for the naked eye. Clear? So basically to convert an image from spatial domain to frequency domain, the main aim is to find out what components or how much is the low frequency component in that particular region and how much is the high frequency component in that particular region of the image. And again the question may be asked, like, why DCT, why not DFT, why not wavelet? DCT for two reasons. One of them is it clearly distinguishes between the low frequency and the high frequency component, as we'll see in the later images. And secondly, it gives at the output all the coefficients are real coefficients, since it is discrete cosine transform, so it deals only with real coefficients, unlike DFT, which at the output gives complex coefficients. Okay, then that is the output of DCT is given to a quantizer. So first we'll look into what actually happens at the output of DCT, then we'll move on to quantizer. So let us assume this is my image, and as you can see there are three regions, for example, have been shortlisted: the eyebrow region, the eye region, and the nose region. There are chunks or regions of size 8x8 which have been highlighted, which will be further proceeded for compression. So as you can see, this is the eyebrow region, and the numbers given in this blocks are intensities. It is an 8-bit image, means each pixel is encoded using 8 bits. Then the intensity will vary from gray level 0 to gray level 255. Then this one is for the eye region, and this one is for the nose region. Clear? So these are the three areas which I have taken as example. Now these are the original image. Matrix A is your eyebrow, matrix B is your eye region, matrix C is your nose region. On that, after performing DCT, you will observe that the top left coefficient, which is 174, which is the highest of it, highest amongst all other coefficients, that is the DC coefficient, the DC component of the region. DC component means the frequency is 0. Frequency is 0 means what? That there is no change in intensity. Then the coefficients adjoining the DC coefficients are the low frequency coefficients. Even those you will observe, those are the magnitude is high. And as we proceed towards the bottom right coefficient, which is almost 0, which indicates that these are the high frequency components. High frequency means the matrix starts from DC component, then to low frequency component, and finally ends at the highest frequency component. The high frequency components on the in an image, as I stated earlier, are the smaller details which are not perceivable for the naked eyes. So what we need to focus on, just the DC component and the low frequency areas which we need to retain, and the high frequency areas which we can quantize them in such a way that they become negligible and hence can be ignored. So that is the idea behind using DCT, and that is the main idea behind Jpeg compression technique. Right? So these are the output of DCT, and then as we know, the output of DCT is fed to a quantizer, which is also fed by a quantization table. So we'll have a look at the quantization table. These are the quantization tables. So what happens is, each DCT coefficient is to be divided by the corresponding quantization table coefficient. Right? So the first coefficient of the DCT output was the DC coefficient, that was, let's say for example, 174. So here it has to be divided by 1. The DC and the low frequency components, as you will see, are to be divided by 1. As we go further towards the high frequency components, then the the quantization coefficient increases gradually to 2, 4, 8 and 16. Means they are to be highly quantized or highly to be approximated or highly to be decimated as the quantization coefficient increases, so that to make them further negligible. This is the table used for when you want to go for low compression. And then the output of division is rounded off to the nearest integer. Alright, and this table is used when we want to go for high compression. As you can see, just the DC value is divided by 1. That means it is retained as it is. So why is it retained as it is? Because it carries the maximum useful information about the image part. So that is not quantized at all. What is quantized? The low frequency regions up to a certain level, and the high frequency parts up to very high level. As you can see here, for high compression, for high frequency region, the quantization coefficient is 256. The output of the DCT is to be divided by 256 and then has to be rounded off to a nearest integer. So these are the quantization tables. So after being passed through quantization, the coefficients are collected in zigzag manner. Starting from the DC component to the highest frequency component, the coefficients are collected in zigzag manner. This is to convert a two-dimensional array or two-dimensional matrix to a linear array. The coefficients are collected in a zigzag manner. Then on the coefficients collected is performed Huffman coding, that is your entropy encoder. Huffman coding is already covered in digital communication in 6th semester. If you still want a revision of that, I can cover a problem by a short video. Just let me know, then I'll record a video for that as well. I'll cover a problem on Huffman encoding, or else if you have a book, in that book also Huffman coding will be covered. At the output of Huffman coding, each intensity is encoded by a binary code, and that binary code, the length of the binary code will depend on the probability of that code appearing in that image region. As you know, that is how the Huffman coding works. It works on the probability of the symbols. Higher the probability of any symbol occurring, shorter will be the code for that particular symbol. Lower the probability of any particular symbol occurring, longer will be the length of the code. After that, it is given to a line encoder. Line encoder, we have got run length encoding. For run length encoding also, I will be uploading a short video as to what is run length encoding. Clear? That is then transmitted. And okay, so here we have for run length encoding. Now let's say this is the strip which we need to transmit. There are long streams of zeros and ones to be transmitted, right? So rather than transmitting 9 zeros in a line, what can be transmitted is 0, 9. That means code 0 has to be transmitted 9 times. Similarly, if there is stream of ones of length 4, then the same can be written as 1, 4. That means code 1 has to be transmitted 4 times. Then 0, 4, that means code 0 has to be transmitted 4 times. This all will come at the output of the Huffman encoding, in which each symbol or each intensity is encoded depending on its probability and is converted into a binary code. So binary code, when we write it in serial way like this, And if there are long streams of zeros and ones, it can be converted in this way. Rather than transmitting so many bits, as you can see, the coding result 0, 9, that means 0 has to be transmitted 9 times, 1 has to be transmitted 4 times, and 0 has to be transmitted 4 times. So this is your run length encoding, right? And this is the output of Jpeg. Image A, that is the original image. Image B with 10:1 compression, and image C with 45:1 compression.